Our next example of Gauss's law applications is the electric field due to a conducting, uniformly charged infinite plane. But first, let us briefly review the properties of ideal conductors. First, we know that there are many electric charges available to move freely within a conductor. And so if a conductor is in a region where there is electric field, those free charges will experience electric force and will move until they stop experiencing any force. That will happen when the net electric field inside the conductor is zero. What happens is that those charges, by rearranging themselves, create a secondary electric field which cancels completely the external. So we say that there can be no net electric field inside a perfect conductor. Then we can select the Gaussian surface S, and we can apply Gauss's law for that surface by calculating the electric flux, which is the surface integral of E dot dA. And given that the electric field, the net electric field inside the conductor is zero, the electric flux will be zero, and so will be the charge, the net charge enclosed by that surface. We can take another surface S1, and the net charge enclosed by that surface S1 will also be zero, because again, as long as that surface is completely within the conductor, the electric flux through it will always be zero, due to the fact that the net electric field inside of a conductor is zero. As a result, we say that there is no net charge inside of a perfect conductor. Any unbalanced charge that might be residing on the conductor must be along its surface. So now let's go to our example. We will calculate the electric field due to charges that are uniformly distributed along a conducting infinitely large plane. First, we see that the charges will be distributed along the surface, the top and the bottom of the sheet, but there will be no charges, no net unbalanced charges inside, and that's what makes it different from the example of the non-conducting sheet where the charges were bound throughout the whole sheet. So we'll write that there will be no net electric field and no net charge inside that conducting sheet. We will be forced to consider its thickness as a consequence. The surface density again will be defined as the charge per unit area. We will define that surface density for the top layer of charges, sigma is equal to dq over dA, and there will be surface charge density for the bottom layer, which will be the same. Sigma is dq dA. Again, at any time, if we want to know how much charge resides on an element with a given area, we'll just have to multiply sigma and that area dA, and that will give us the charge. The electric field distribution is very similar to that for a non-conducting uniformly charged infinitely large plane. We know that it's going to be away from the sheet, directly perpendicular, and the magnitude of the electric field cannot vary along the surface. Here again we have the same type of symmetries. We have the cylindrical symmetry. In other words, when we rotate the plane, it coincides with itself, so the electric field must have that same cylindrical symmetry. And also, if we pull or push the plane along, again it coincides with itself, so the electric field cannot vary in magnitude. We will select again the Gaussian surface. That is a cylinder, but now the base of the cylinder will be placed exactly in the middle of that sheet where the net electric field is zero. Of course, that surface will enclose a charge which we can calculate as sigma, the surface charge density, from the top layer of the sheet multiplied by the area, the base area of the cylinder. For the sides of that cylinder, we will have the area vector for any surface element will be perpendicular to the electric field lines, and so E dot dA again will be exactly zero. Here we will have to treat the base and the top ends separately. So for the cylinder top, the area vector will be parallel to the electric field vector, so we'll have E dot dA equals E dA. And for the cylinder base, since we have no net electric field inside the conductor, E dot dA will be 0. There will be no electric flux through that base. And now we're ready to apply Gauss's law. We calculate the electric flux as the surface integral of E dot dA. Of course, of all three different types of surfaces, the base, the top, and the side, the only non-zero integral will be the one over the top of E dot dA, and that has to be equal to the charge that was enclosed within the surface S over the permittivity of free space epsilon naught. We saw that the electric field does not change its magnitude, so we can take it outside the integral, and we'll have E integral of dA integrated over the top of surface of the cylinder, which will give us simply E times A, and that has to be equal to sigma times the base area of the cylinder over epsilon naught. We cancel A, and we get for the result of the electric field due to a conducting uniformly charged infinitely large plane to be sigma over epsilon naught.